So fallacy number 2, latency isn't a problem. Now, when talking about network latency, it's the time to cross the network in one direction. When talking about latency, most developers are familiar with a concept called round-trip time. Round-trip time is, for example, when looking at a client talking to a server, is that we'd measure the time that it takes from the invocation until we get a response. The reason why we don't focus on round-trip time when talking about distributed systems is because it intermingles things like serialization and deserialization, which really have nothing to do with the network, and the actual processing time on the server. So when we're looking here specifically at latency, we're looking at, given that we've serialized everything and we're ready to go to the network, how long does it actually take to get from the client to the server? So the thing is, and in that coding model, we kind of assume it's effectively 0. And usually when we run things on our own machine, it really is effectively 0. But the thing is that as you're building a more geographically distributed system, whether it's starting from a LAN environment and then crossing to a wide area network or the internet at large, you end up increasing orders of magnitude at each step in terms of how slow it goes. So just to give you a sense of what those order of magnitudes are, and you have this printed up in front of you, there's this nice table that fellow speaker created that normalized all sorts of computing operations to the time of one CPU cycle, where one CPU cycle was scaled to being 1 second. Why? Because as human beings, we're not really wired to understand the difference between nanosecond, microsecond, and millisecond. We hear all of those things. We just hear second, second, second. And it's like, yeah, it's pretty fast, even though there are 6 order of magnitudes difference between them. So with CPUs that are doing roughly 3 billion operations per second, if one CPU cycle is 1 second, accessing main memory from the CPU is 6 minutes. All right? 1 second, you find something in memory, that's 6 minutes. All right? Give you a sense of the kind of difference that we're talking about. You need to go from memory to disk. You're jumping from 6 minutes to potentially 6 days. All right? Not minutes to hours, minutes to days. It is that much slower just accessing a drive on the same machine. When scaled with 1 second equals 1 CPU cycle. You want to start going outside of your machine to the big bad internet, things get a whole lot worse, a whole lot faster. So you want to cross the internet, let's say from coast to coast in the continental United States, San Francisco to New York. The actual number is roughly 40 milliseconds. When you scale that, that works out to roughly 4 years if one CPU cycle is 1 second. Right? So one remote call, continental US, 4 years compared to the 1 second CPU operation. All right? Just to go back, this, newing up an object, is on the order of seconds. This, making a remote call to something else, years. And that's what's so dangerous about our programming models, that you have developers that talk on and on about ways in which they can improve the performance of their system. The number one issue is that 2 lines of code sitting side by side can have this difference of seconds and years in terms of a performance characteristic. And it becomes that much harder when we use modern day programming techniques like dependency injection. Who uses dependency injection, by the way? Great, you all should. It's a great technique. Don't get me wrong. It improves the testability of our code and decouples things. All of that's great. But the thing that it does is it hides this line of code, right? You just declare a dependency on an iSomething service. And you don't know when you invoke a method on the iSomething service, whether that's going to be a local call or a remote call, right? So in essence, we create this model where as we're programming, the performance at runtime is better and better hidden. And then we start deploying things to production and users start playing with the system and they say, the system is slow. And now we're kind of stuck. It's okay, where exactly is the system slow? What is the culprit? And we've done such a good job at hiding from ourselves where all of these remote invocations are that it becomes that much harder to find it. Let's just go down this table a little bit more, all right? So if we want to go from San Francisco to the UK, now we have a 2x hit. Instead of being 4 years, it's 8 years. You want to go San Francisco to Australia, you're talking about 19 years. And this is the best case scenario. What if the packet doesn't arrive? Why? Because it's network. And you have to retransmit. So until the time that TCP figures out that it needs to retransmit and then it retransmit, you're probably on the area of a century or so. All right? So best case scenario, maybe 5 to 10 years, scaled to 1 second. Worst case scenario, and this isn't worst case, just a network retry, 100 years. Let's say something really bad happens and you have a physical system reboot, an actual machine goes down, it doesn't have power, and needs to start up again. If one CPU cycle is 1 second, a physical system reboot can take on the order of 32,000 years. All right? Millennia. Why do I drive this point home? Because it's really the only way that us as human beings, even as technical people, can really understand just how bad code like this can be to the performance of your system. All right? And again, I'm not saying don't use dependency injection, but understand that first law of distributed objects. Don't distribute. There's a whole lot of physics backing that up. The speed of light is kind of a hard boundary. And yeah, we're getting better in that, physical systems still reboot, but we have slightly more reliable hardware. Except for those of you running in the cloud. Who's running in the cloud? Okay. You know what the idea of the cloud was? You get many more machines that are less reliable on average than the kind of hardware that you'd buy for your own data center. That's kind of the idea. It's that you get machines on tap. You need 1,000 machines, you turn the tap up a little bit higher. And you can only build those kind of machines at scale if you're willing to sacrifice some of the reliability. So they say the difference between an on-premise environment and a cloud environment is the difference between pets and cattle. All right? Pets are named. You take care of them. You feed them. You take them to the vet. They're these named creatures, and you want to make sure that they're well taken care of. Cattle, it's like 100 head of cattle, 200 head of cattle. One of them falls over, whatever. That's the cloud. All right? So the likelihood of something bad like this happening to you in the cloud actually goes up as compared to when you're running on servers in your data center. And yes, all of the cloud providers are trying to make sure that everything is more reliable all the time, but it's important to realize that when bad things happen, you're going to be paying orders of magnitude in a scaled element of years, decades, and centuries for every one of those remote calls that you're making. So for those of you who might have been wondering before this class started, what do I think about microservices and making lots and lots of remote calls, there's your hint. All right? Lots and lots of remote calls are bad. They've pretty much always been bad. Just to give you an idea of the source of these fallacies of distributed computing, 20 years in internet time is a very long time, right? The thing is that these first 4 fallacies were actually written quite a bit earlier. They were written in the late 70s by 2 engineers from Sun Microsystems. And you can imagine that networks were pretty crappy back in the 70s. So yes, networks have gotten a lot better, but the thing is that the systems that we're building are relying on networks quite a bit more heavily than they were before. So these ideas that these problems are going to cause pain in systems, not new ideas. They've been around for decades. They've held up for quite some time. And when talking about the network not being reliable or latency being an issue, it's important to understand that it's not, it's had a good 10, 20, 30 years to be resolved. And computing has changed massively during this time frame. But if something is held true for 30, 40 years in computers, there's a pretty good chance it's going to hold true for quite a bit longer. Caveat, there's this other thing that's on the, you could say it's on the horizon, it's halfway here, quantum computing. The idea of having quantum bits that you flip a bit on one side of the planet and instantaneously another bit on the other side of the planet flips with absolute zero latency? Yes. When we're all doing quantum computing, then physics has fundamentally changed, and then you can throw out this table and not have to worry about the years that it takes to cross from San Francisco to New York. All right? But until such time as we're all working on quantum computers, these laws of physics hold, and we would do well to not fight physics. You usually don't win when you fight physics. It's been around a while. So coming back to that idea of remote objects, don't do remote objects. Don't do things that look like remote objects, quack like remote objects, and walk like remote objects. All right? Yes, question?
Isn't messaging remote object?
Isn't messaging remote objects? So message queuing is slightly different in the sense that there isn't necessarily this concept of invoking a method on a remote object and definitely not waiting for a response. So it is more similar to a post office where you're dropping a letter in the mail and yes, at some point in time it will be delivered. So it's very different than picking up the phone and chatting back and forth with an object. All right? So
serializing messages that go on the wire.
So yes, there is the same behavior of serialization that happens of the payload, whether we're doing a remote object call or we're doing a queued delivery of the payload that we're sending. But here it's not so much about the payload that we're sending as the nature of the interaction around the payload. So we'll talk a lot more about messaging patterns. But in terms of the nature of the communication, it's the what is my level of familiarity and coupling to the thing that is on the other side. And usually when we think of something like dropping a letter into a mailbox, that is a lower level of coupling than picking up the phone and calling somebody. All right? So it's the nature of the interaction. Now, a few more words on remote objects. Back in the day when remote objects started, people were so enamored by object orientation that the concept was that if you needed to access even a property on an object, that would be done remotely. That you would do A dot B, and referencing that B would result in a remote call to the other side and get you some data back. Luckily, as an industry, we've realized that's a bad idea, and we use data transfer objects as a pattern to say, okay, I need a bunch of data, and then the server gives me back a pile of serialized data, rather than the regular A dot B, A dot C, A dot D as a way of getting the data that I want, each of them with a remote call. Now, the thing about almost every bad idea, you give it enough time, it gets reinvented under a new name. So there's this thing called object relational mappers. Who's used an object relational mapper before? Okay, a lot of you. So when talking to a database, you get this nice object-oriented abstraction where you load up an object, and there's this great feature, it's called lazy loading. Probably familiar with it. Where the object gets loaded from the database, but not all at once, right? Some properties get loaded right away. Other properties are sitting there waiting to be dereferenced. Usually these are collections, right? So if we have a parent.children type of model, usually the children are not loaded immediately. And now we're kind of back in the area of remote objects. So if you access the parent dot some property, parent dot another property, those invocations are in memory, they're very fast. But if you decide to for each over the list of children in that parent object, all of a sudden that ORM says, hold that thought, Off it runs to the database, does a remote call. Remember, we're talking years potentially. Comes back, says, I have it for you. You must have not even noticed that I was gone. Because that's the way that we code, right? For each child in parent.children, do something with the children. We code under the assumption that all of that is effectively immediate, that the latency is effectively 0. And that's that bad remote objects thing again. Now, this may lead us to a place where we're saying, oh, okay, well, don't cross the network if you don't have to, obviously. But if you do have to cross the network, for example, you're loading up a parent and it has some children, and you know that you're going to be paying such an enormous tax to bring those children objects on another round trip later on, it might make sense to bring back those extra pieces of data up front with you. Now, the problem if you take a solution approach to this is, well, wait a minute. If I load the parent and the parent has a collection of children and I eagerly fetch all of the children, what happens if those children have their own children, right? And then I load up all of their children and the graph starts to kind of explode. And then just to show a very simple list of names and phone numbers on a screen, now I'm bringing back 5 terabytes of data from the database, right? It's ridiculous. Which is why we have fallacy number 3 about bandwidth, which is serving as a balancing effect against fallacy number 2 that talks about latency.